Open a browser to research a complex problem, and within minutes, you are looking at dozens of open tabs, scattered articles, and disjointed text fragments competing for your attention. There is a persistent assumption in educational technology that providing students with instant access to multiple hyperlinked documents automatically improves their ability to construct and understand a complex argument. Empirical data proves the opposite. Research by Britt and colleagues demonstrated that presenting multiple documents via hypertext offers no inherent benefit over linear text. In fact, providing a scrambled hypertext structure actively causes a deficit in cognitive processing. The physical speed of navigating between URLs creates an illusion of productivity, but rapid clicking does not equate to the deep cognitive retention required to actually learn the material. Raw digital access to information does not automatically result in the intellectual synthesis of that information. True digital comprehension, what researchers call discourse synthesis, is not a default biological state. It must be intentionally engineered from the ground up. This engineering requires three dependencies. First, interface constraints restrict how information is displayed to manage cognitive load. Second, task design dictates the specific actions required while reading. Third, cognitive skill represents the user's baseline literacy in evaluating document credibility. If any one of these three variables is missing or poorly implemented, deep learning within a digital environment collapses. To isolate exactly how the interface affects learning, psychologist Jennifer Wiley designed a study asking students to determine the historical causes of the Irish potato famine using a set of online documents. The left side of this composite image shows the baseline test condition. Students used a standard single-window web browser to read through the multiple historical texts. They largely failed to synthesize the data. A single-window setup forces a high-load toggling action. Every time a user clicks back or switches to a new text, their working memory degrades, making it highly difficult to hold facts from document A in mind while reading document B. The researchers introduced an interface intervention, moving the students to the forced dual-window, side-by-side presentation you see on the right. The dual-window interface only improved performance when the researchers simultaneously assigned an argument writing task. When students were just told to write a narrative, the interface change did nothing. Argument writing works because it forces the user to aggressively transform, organize, and connect the information across sources, rather than passively scrolling and extracting isolated facts. Providing a flexible multi-window interface is functionally useless unless the assigned task physically forces the user to integrate the data. Interface layout is only half the problem. The cognitive challenge compounds when users have to evaluate whether the digital information they are reading is actually credible. This overhead photograph shows the desk of psychologist Jean Piaget. Experts operating in physical environments rely heavily on spatial organization and physical artifact cues to gauge the value of their sources. Readers traditionally rely on physical heuristics to guide their comprehension. The weight of a textbook, the texture of the paper, or the prominent logo of a publisher instantly communicate the document's intended purpose and reliability. The transition to digital screens destroys these cues. The uniform nature of web browsers completely strips away traditional physical indicators of hierarchy and trust. On a screen, a highly rigorous peer-reviewed journal and an amateur teenager's blog look visually identical to a novice. They share the same font, the same margins, and the same backlight. Digital interfaces inherently rob users of the sensory cues that human brains traditionally require to establish source credibility. Without these physical cues, novices struggle to evaluate websites. Researchers Brem, Russell, and Weems documented this by observing high school students attempting to categorize online sources. The students defaulted to absolute thinking. They attempted to cleanly categorize sites as either real science or deliberate hoaxes, entirely missing the nuance of biased reporting or institutional motives. Users rely heavily on surface markers. They will accept claims simply because generic footnote icons, scientific jargon, or a doctor title are visually present on the page, without verifying the underlying support. Further studies by Easton confirm that users base credibility on perceived authority and topic familiarity, metrics that are easily spoofed in online environments. Experience with the web does not fix this. Heavy internet users are faster at executing search queries, but they are no more accurate at evaluating the credibility of the results than novices. Without structural intervention, digital novices lack the sourcing and corroboration skills needed to survive online research. The engineering solution to this deficit is computational scaffolding. Software must physically force users to execute evaluation heuristics during the reading process. This interface belongs to the Sorcerer's Apprentice, a tutoring system designed by Britt and Angliscus to teach library and information science heuristics. The core mechanic of the system is restriction. It decomposes the complex task of evaluating documentation into a mandatory sequence of simple subgoals. The UI forces the user to physically drag text strings into structured metadata bins for categories like author or motives. The software literally will not let them proceed to the essay writing phase until they correctly evaluate the source. This engineered friction yielded clear results. Students who used the system wrote significantly better, causally connected essays compared to a control group that performed unstructured reading. Software interface design can successfully externalize cognitive load, forcing novice users to read, evaluate, and source information exactly like domain experts. These findings dictate clear macro implications for educational technology, instructional design, and the architecture of online classrooms. There is a critical distinction between web experience, navigating URLs quickly, and true digital comprehension, which requires synthesizing disparate data points into a coherent model. Learning from the open web requires reading within a strict, predefined problem-solving framework. We have to recognize the stark contrast between open-ended, unstructured web browsing and a targeted, constrained digital learning environment. Providing maximum freedom on the web actively hinders deep learning for the average student. The web is not a learning toy that inherently imparts knowledge simply through exposure. Future educational platforms must simultaneously integrate exact interface constraints, directed synthesis tasks, and explicit cognitive scaffolding. Instructional designers must abandon unstructured web assignments in favor of introducing intentional, structured digital friction. True digital comprehension is an engineered output, not a biological human default. If we want to change how students synthesize information online, we have to redesign the architecture of the screen itself.